So, welcome everyone to the 18th lecture on statistical theory for deep learning. Sorry I'm 2 minutes late, but this was, well, say it this way, this was due to the late arrival of the airplane, because the lecture before was needed 2 more minutes, and so I lecture almost not free. Okay, we are at the end of chapter 3 about neural network generalization, and I presented a major theorem, which is a theoretical bound on the VC dimension of sets of deep neural network with ReLU activation function. It's theorem 3.7. You have calligraphic F be a class of deep neural networks which represents or implement functions from RD to R. They have depth L. They have W many weights or possible non-zero weights. So it might be more weights or more connections, but all other connections are permanently zero. So this is the number of connections which might take on non-zero weights, but don't have to. And I have a ReLU activation function. And then the VC dimension of the class of the corresponding subgraph is less than a constant times the depth times the number of weights times the log of the number of weights. And this constant does not depend, of course, on the depth on the number of weights, but also not on the number of neurons in the network. But of course, this number of neurons is somehow upper bounded by the number of weights, because if you have more neurons than weights, then you will have one neuron which has no connection to all other neurons, so you can basically forget about it in the definition. And I presented already the proof idea, and proof idea, it's somewhere, okay, let me see the right slide here. We use some mysterious lemma. The lemma says the following: suppose you have m polynomials of degree at most d in w many variables, where we assume that m is greater or equal to w. Then the number of values which the vector sine of first function of a, sine of second function of a, and so up to sine of m function of a. So this is an m-dimensional vector, and I define the sine such that the sine of a number is 1 if this number is greater or equal to 0 and 0 else. So it's an m-dimensional vector of with m components being either 0 or 1. There can be at most 2 to the power m of these vectors, but the point is I can give an upper bound on these vectors by 2 times 2emd divided by w, and the whole thing with exponent w. And using this lemma, we have already seen that for the proof we can show, it's obvious to show the following. I write my functions, my neural networks, f from Rd to R, as an f with an additional parameter theta, where theta is the vector of all weights. So I have w many, so theta is a value in R with exponent w. And I have x1 to xm in Rd, and then I have to show, and that is the remaining thing which we have to show. As soon as I have shown this, we have already proven the theorem. I need to find a partition PL plus 1 of R with exponent w, such that for each set of this partition, the f with eigenvalues for x, x1 to xm, so these are m functions, and the weight vector varies theta in Rv. These are our polynomials of degree at most L plus 1, and this number of sets in this partition is less than 2 to the power L times 2eml with exponent w times L. Okay, so you see what is missing. We have to show this, I have to construct this partition, and then I have somehow to show you, tell you where does this mysterious lemma comes from. And let's stay with this start start with this mysterious lemma. I have already explained that for degree, for a number of variables, w equal to 1, the whole thing is trivial. But now I need the general case. And I don't give this proof because this proof is rather involved. You can look in the book of Antonin Bartlett, which is cited in the lecture notes, and you will see you will not find a complete proof, but you will find most of the proof, and then there will be some reference to the literature, which goes again deep in mathematics, but I think I can present you the main idea. So the sketch of the proof of lemma 3.2. So this is our case, this number of different values which our vector achieves or can take on. And the first thing is that you can show if you slightly modify your polynomials, then you can say that I don't have to consider all a in R with exponent w. Instead, I consider only those a where f1 of a up to fm of a are non-zero. So I can show this is the same as, that's the sign of f1 of a to the sign of fm of a. And a is in R with exponent w, but not in one of the sets like Q1 to M. And maybe I make now an A bar. Where I have of U F I A bar. Okay, we are here. I have to close this bracket. Does this make sense? Well, look at the example W equal 2. So I'm in 2 dimension, and maybe I have M equal 4. So I have 4 functions. And now I can look at what is in this 2 dimension, I have the first dimension, I have the second dimension of A. I look at the set of points in this 2 dimension where one of these Fi is equal to 0. And I assume this might be, for instance, some kind of line that might be F1 of A. Then that might be 2 of A to 0. Then maybe this one is not a line, it looks more like this. 3 of A to 0. And then maybe I have one more. 4. And now I also assume that these lines subdivide my plane in 2 areas, and in one area the function is positive, on the other one it's negative. So for instance here, the 3 of A is greater 0 again. Greater equal. And then maybe here here maybe F2 of A is equal to 0. And then on the third line, here, F1 of A. And now if you look carefully, then you will see in this example, this equality does not hold. Because you have one single point, the single point is here, where F1, F2, and F3 are greater or equal to 0. So the sign of F1 of A is 1, the sign of F2 of A is 1, the sign of F3 of A is 1, the sign of F4 of A doesn't matter. But you find no other point on the whole thing such that F1, F2, and F3 have a sign 1. So in general it does not hold, but what I can do now, if you think about the whole problem here, the whole problem, if you look at the definition of decay, definition of decay was without this point, yeah? Then you look at this number of maximal vectors, and then you have a number of A's, basically K-A's, where for which these maximal vectors occur, or these vectors occur. So I'm talking about, basically I have here points, finitely many. Couldn't be more than 2 to the power n, but finitely many points here. And then I'm just starting to change slightly my polynomials by maybe I add or I subtract. I think I subtract some small number greater 0 from F3, from F2, and from F1. And then those points which are on the border, they will be on the part, or I make it such that those points which are on the border, they are on the part where the function is greater or equal to 0, but those points which are not on and those points which are on the path greater or equal to 0, they stay in this because I moved this whole part a little bit in this side away from the part where it's greater or equal to 0. And those points which are away, they have some positive distance to the border. So if I make this small enough, this case does not occur anymore. That's the first trick. Okay? And how does this help? Well, this helps a lot, because now let's consider the number of connected components of a subset of RWV. So let CC of A be the number of connected components of A subset R with exponent on W. Connected components means it's a maximal set, so set of maximal, so set maximal with respect to the subset relation, such that for each 2 points in this set you can find a curve which starts in the first point, ends at the second point, goes throughout this set all the time, and is continuous. Well, but if you have something like this, if you stay completely in one of these connected components here, well, you see what the number of connected components is. These are a lot here. But if you are, my picture is not good yet, but you see, this is subdivides my space in and I have this one too. So how many connected components do we have? That's a test whether you understand anything what I'm talking about. more than 3 or something like this, yeah? I'm attending a wedding of my brother-in-law in July in the US. And in the US, they have a wedding rehearsal. So they make some, on the day before, they make some rehearsal in, I don't know whether you know the English word, in German it would be Probe. So they make like a rehearsal for the wedding, yeah. And then the question is, do you really need a wedding rehearsal there? And my wife told me, okay, I told her totally, no, I won't attend the wedding rehearsal, that's ridiculous, yeah. Because who needs a wedding rehearsal? And then she followed some text in the social media where people ask or describe that in the US they have a wedding rehearsal, and all other people from other countries told, are they totally stupid, yeah? And I heard once this story about a Senate candidate, which was one of the Trump candidates, and who lost against the Democrats. And then after the election, one of the leading Republicans told, well, if this guy would be able to chew a chewing gum and walk straight forward at the same time, then he would have won. But so, and here it's also a simple test, but okay, but you can see. So how many do we have? What are the connected components?
Can I count to 8?
You count to 8. So you see, maybe you have 1 here, yeah? 2 here. You have 3 here. You have 4, yeah? 5. 6. Oh, I'm getting more, yeah? 7. 8. Maybe 9. No, correct? So one component is, for instance, this one here. So we have. But you see, if you are in one of these components, connected components, of this set, yeah, then the sign doesn't change. Because in order to change the sign, you have to run over one of these lines, where one of the function is 0. So you see immediately that's less than the number of connected components of this set. A bar W and A from A bar to 0. And basically, you need a proof for this one. Not really difficult, but basically this one is clear. And now you see what you have to count. You have to count the number of connected components of these sets here. And how to count some number of connected components. Well, it's a number of connected components of some set difference. And then you come up with some funny lemma which tells you you have a set difference. You write this as a set difference with respect to the union of I running from 1 to m minus 1 and the m set, yeah? You need a number of connected components. If you just reduce one, introduce it to the other set, and then you apply it recursively, and then you come up to some funny thing, which is non-trivial and not completely proven in the Bartlett book, because he uses this one lemma from algebraic, from topology, how this number of connected components behave if you subtract, if you make a set difference. And of course you also have, I don't know whether they need a special form of the sets, that they are 0 sets or not. Don't remember this one. So you can reduce it to the number of components, connected components of intersections of the 0 set. A is W, F is 0. S is a subset of 1 to m. The empty intersection is just the whole space. And now there's one other trick, because you can make a size restriction of S. Because you can show, again, you maybe modify your functions a little bit, your polynomials a little bit, that more than w of these polynomials do not have 0 at the same time. So this size is less than w. Next trick. Okay. And you can imagine there might be some proof showing something like this here. Not so, shouldn't be so difficult if you are able to deal with connected components of set differences. And there is a proof. Okay, how does this help? Well, this one you can say is the same that all of these polynomials fi, where I is in S, have a 0 at the same point. And I can also say, okay, instead I sum them up squared, and then the sum of squared must be 0, which is the same. So I got this one. I have this same sum. Maybe I don't write it to save some time here. Then I have the A in R W, sum I in S, Fi squared, 0. You have this. And now you see my sum of squares. Well, my Fi's are polynomials of degree, what was our degree? D. So this is a polynomial of degree d squared. And now you look in the literature and find the following lemma, or basically you find a general theorem, and you conclude from this the following lemma. The lemma is if f from Rd to R is a polynomial of degree L, then the number of connected components of the set of all 0 points of this polynomial that's less equal L with exponent d minus 1 times R plus 3. So find such a result in the literature about algebraic topology. And you don't find this result, you find a more general result, and then you have to understand the more general result and see that this applies. But you can imagine something like this exists. Yeah? It's clear, multiply polynomial. If you look at the points of 0, the components will, the connected components number won't be infinite. In particular, for d equal 1, it's trivial, yeah? Because the number of connected components will be d plus 1. No, it will be L plus 1. That's obviously more than L plus 1. Now I can say this is this. Again, I have my sum as less than 1 to n. Cardinality of S is less equal to W. And we apply this with d squared. And the degree is L, yeah? So L is equal to d squared, and d is equal to W. So I have a d squared times W minus 1 good, you learned, yeah? You didn't tell me my mistake immediately. Where's my mistake? I detected it already, so now you can tell me. That's correct. The square of a polynomial of degree d is a polynomial of degree d squared. 2d, yeah. Must be 2d. So you see here it must be 2d. And here it must be 2d. Now we have to compute this sum, but it's just the number of the sets we need, because the term we sum up doesn't depend on S anymore, yeah? And you see this, I can count how many of these sets exist. Well, I can count the set with 0 elements, 1 element up to W element, the subsets of a set of size m, where they are of size m, they are m to the power I, m atop I, many of them, binomial coefficient, and then you can make here a 2 times make an upper bound by 2 times 2d with exponent v. And now you make one trivial bound, which we know. You know already. What do we know about this sum I equal 0 to w, m to the power m to the I? Well, I multiply this sum with w divided by m, with exponent w times this sum. We had this bound in the proof of the Wapnick-Cheremenko theorem, m to the I. Then you multiply this in, and we assume that W and W is less equal than M, and that the W is less equal than M here, so that's less equal than 1. So if I replace this one by I, exponent I, it gets larger, times 10 to the power I, and then I make the upper bound larger by summing up to m. And then I use the binomial theorem, and you see this is 1 plus w divided by m with exponent m. And then you make 1 plus x less equal e to the power x. So the whole thing is less equal to the power w. So you see the sum is less equal than m times e divided by w with exponent w. So we have m times e divided by w with exponent w times 2 times 2e with exponent w. And if you look at this one, this should be all correct bound. Correct. And we are done. Questions? So you see, I think it's a nice proof. This one is actually not difficult to show. This one is obvious. Here's the first miracle happening, but you can imagine it goes. And here's the second miracle happening, but you can imagine something like this holds. You get the last section. But to really prove this theorem, no chance. Because this goes into other lectures. which we don't know, or I don't know, so no chance. Okay, done. That was the first part. Now what remains to do is to prove the missing part of the proof of theorem, of our last theorem, which is to construct this partition. And that's actually not difficult, as you will see. And again, we will use our lemma, which we have just proven or tried to prove. So the missing part theorem 3.7. And instead of constructing directly the partition PWL plus 1, so that all so that my neural network at m fixed points evaluated is a piecewise polynomial of degree L plus 1 for my neural network. I construct recursively partitions P1 to P2 until PL plus 1, such that the output or the activation of my neural network as a function of this fixed x1 to xn, or with these fixed values for x1 to xn, and then as a function of the weights, are piecewise polynomials with respect to this partition of degree on level I of degree, or on the level small l on degree of degree small l. So we construct recursively, partitions P1, P2, P1 plus 1. Such that all activations and my activations, and that's the capital L, on level L in 1 to L plus 1. And these activations, well, depends on how many neurons you have. I have a first activation, A1, level L, second activation, 2 of level L, until I have some number of neurons, which I maybe use the notation R index L, of neurons at level L. are for input x. My input x is one of my x1 to xm. As a function of the weights, that's wrong. And I should be on all sets, all A all sets, equal to a polynomial of degree L. This way and then I have to count how many sets are in this partition, and I got my assertion. Well, any idea how to do this for small L equal to 1? The activations on the first level. How can I partition the weights such that they are linear polynomials as a function of the weights? Well, it depends what are the activations on the first level here. Maybe a picture helps. You have your x. X is one of the values x1 to, say, d components. You have an additional 1. Then you have a first neuron. You multiply each of these inputs by a weight, sum up, and then apply the redo activation function. Then you have a second neuron, and so on until the last neuron. And for all these neurons, you do it in the same way, but with different weights here. And then you do the same thing again here. Maybe let's do it with two neurons, with 2 levels here. Or here. So let's say we have all levels equal to 1. Here. And then finally, to sum up. That's it. Now the question is, where are the activations? The activations of the neuron, in contrast to the output of the neuron. Where's the output of the neuron?
Output of the neuron is the arrow going out.
That's the one you hear here. And what's the activation?
And the activation is the sum.
Just before, yeah. So the activation is the sum. So what? How can you choose a partition of R2 or no of the weights such that this sum are linear polynomials.
I need to make sure that ReLU either takes the 0 value or the maximum value. So
You make sure that the ReLU either takes the 0 value or the maximum value. That's the right answer if I want to get that the outputs are polynomials. But at the moment I don't want that the output of the ReLU is a polynomial. I need that the input of the ReLU is a polynomial.
It already is.
It already is, so I can choose P1 equal R with power V. For type 1, this holds. P1 is V. Because the star for equal 1 are linear polynomials. Or linear combinations of the input. And now comes your idea here. I make sure, I want to make this also for the output. And I want to make sure I make this partition such that the sign is either plus or 0. If the sign of the input is plus, then the ReLU of the input is just the input. If the sign of the input is 0, the ReLU of the input is 0. Both times the output will be a linear polynomial of the same degree, and then I multiply with one more weights and get P1 plus 1 plus 1. And here you see we can use our lemma again. So if PL minus 1, so if for L element 2 to L plus 1, L minus 1 is the above. Then the sign of the activations of 1, L minus 1 A R L minus 1. So this vector takes by lemma 3.2 on each set in PL11 at most how many different voltages? Many different ones. How many volumes are there? Well, you have to put it with lambda 3 or adapt this to lambda 3.2. Yeah, so you have to deduce what is your W, what is your M for the solution. And so what is the W? And of course, we don't need the exact value of W, we need an upper bound here. I'm using a rough upper bound. Polynomials, and how many variables are there? So my activations are polynomials. Polynomials, and how many variables? RL, you claim, well, no, this is polynomials of the weights. RL is the number of neurons you have.
RL times the number of
Yeah, you want to compute it correctly, you can compute it correctly by counting it, but I make a rough upper bound, I just use W. The total number of. So I use W equal W, yeah. That's easy. Because the other one don't gives me a better bound. Okay, what is the M? How many functions do I have here? RL. I have, or in this case it's RL minus 1, yeah? And what is the degree? D?
big L.
Well, that would be a number bound, but I'm using a smaller. Or do I use a smaller one? I think I'm using a smaller one, or do I use a big? Well, I want to use this degree here. And I don't see at the moment whether I need it or not. Okay, so we can just plug it in. Delta times two times E times, well, M we have, because it's an E, so it's L minus 1. We have said D is L minus 1. I said that W is W. Oh no, and now I make an upper bound here. Rough upper bound. I forget about, because you see what we want to get. I forget about. Where does this M come from? This looks wrong. Because I want to get this 2EML. So where does this M? Oh yeah. You see, I have these activations here, but I plug in the X values, X1 to Xn. So I have these activations for each Xi. And therefore I have an RL minus 1 times M here. Where does it come from? Because we have this one from Xi. This one from Xi. This one from Xi. And I equal to M. So I have M times RL minus how many polynomials. And now I make an upper bound. I assume without loss of generality that this RL minus 1 is less than W, because otherwise I have a neuron which has no connection to other neurons. Then you can forget about this one. I write here L. So we get 2 times 2E times M. L is up exponent W. And now I construct PL by just subdividing each jet in so many so many subsets. Dividing each set in delta subsets. Gives a partition, partition EL. Where on each set, the activations in star are either negative or positive. Where on each set activations on level n-1 non-negative or negative. And consequently, the output of these activations is either equal to the activations or zero. The activation. Zero. And this implies that the activations on level L+1 are polynomials of degree less equal than L. This implies level L are polynomial on each set and now we have it, because now we set we don't see where that PL+1 equal to PL. No, we look directly at PL+1. So PL+1, recursitively constructed, it satisfies 1. By construction. And now we only have to count How many sets are there? The cardinality. Well, you start, you go from P1 to P2 to P3 and so on. So we got the product I equal 2 to L plus 1, cardinality of Pi, cardinality of Pi minus 1, and then we end up with cardinality of P1. And then you see this cardinality each time is less equal, this factor of the cardinality is 2 times is this correct? 2e L is exponent W, then you have it L times 4. And that should be the number which I claimed into, hopefully 2 to the power L times 2em L is exponent W time. And we are done. Questions? So this is pretty simple proof, and all relies on this mysterious lemma 3-point. And of course you can generalize it, you don't need redo, it suffices that you have an activation function which is piecewise polynomial. The original paper by Bartlett was formulated in a more general way. They also proved the lower bound on the VC dimension, which is of the same order. That's all things which we don't need. Questions? Then it's 10:50 and I make 5 minutes break for cleaning it up. Okay, I would like to go on. Maybe I can turn off the. Because we don't need anymore. We had now a chapter on neural network approximation. We had a chapter on neural network generalization. Now I combine the results of both chapters to analyze neural network regression estimates. That's chapter 4. And to define neural network regression estimate, I use the principle of least squares. And to be able to derive some bounds, I present the general result about least squares estimates. Let's give section 4.1. Which basically reformulates or uses the exponential inequality which we have derived at the beginning of chapter 3 to bound the expected L2 error of least squares regression estimate. So I'm in a regression setting. So I have IID, RD times R valued random vectors, which I denote by xy, x1, y1, and so on. Independent identical distributed, RD times R valued random vectors. I assume that y squared is workable. Because of basically two, I have an object which has some property which I want to predict, which is the label or the value of y, and this has some properties x which I observe, and I want to use x to predict y, and I used it such that the mean squared error, so the expectation of alpha x minus y squared is as small as possible, but that makes only sense if y is square integral. And then you have already seen what the optimal predictor is, that's the regression function. So that n from R to R. So if you want to predict the value of y given the value of x, then the best thing in the mean squared sense is to predict the mean value of y given x, and that's just the conditional expectation of y given x equals small x. The corresponding regression function. Then I cannot use this regression function in an application, because in an application the distribution of x, y is unknown, and therefore also cannot compute this conditional expectation. But what I can often do, I can observe data of this distribution, and that's my sample dn consisting of the random variables x1, y1 until x and yn. Dn consists of the random variables x1, y1 until x and yn. Then I choose some function space, for instance neural networks. functions and then we define the least squares estimates of M. M corresponding to Fm. Well, I just look at the empirical alter risk, 1 over n times sum I equal 1 to n f of xi minus yi squared, and I choose the function f from fm which minimizes empirical alter risk. That's what I call M and Quiddle. And it's a function which depends on the data. And that function from, or one of the functions from Fn, one function space Fn, which minimize the empirical alter risk. And then I need something else because as you see in our bounds on the covering number, we use this bound this covering number by a packing number, and then we use this result about the packing number we can bound by using the VC dimension of the subgraphs, but we need bounded functions, and in order to ensure this boundedness, I truncate my estimate. So I said mn of x, mn of x. Again, it will depend on the data. That's some truncation operator, t beta n of mn equivalent of x. For some beta n greater 0, and there I introduced this t big beta n of z. Well, that's z, if z lies between minus beta n and beta n. Okay, write in this form. Z, if minus beta n is equal z is equal beta n, and if z is greater than beta n, then you set it equal to beta n, and if z is less than minus beta n, you set it equal to minus beta n. And then our main result is the following bound. Error bound of the expected true error of this estimate. It's 0.4.1. I assume that instead of a beta n, which depends on the sample size, I assume just some fixed beta because I will assume that for simplicity that my y values are bounded by beta. So that beta greater equal 1. And assume cardinality of y is less equal than beta almost surely. I set beta and equal to beta and define mn as above. Then I can prove the following bound on the expected true error of my estimate. So it's the expectation of the integral of mn of x minus m of x. when I integrate with respect to the distribution of x, that's less equal than some constant c1 times beta with exponent 4 times 1 plus some supremum over all points x1n in D with exponent n of the log of the L1 covering number with radius 1 divided by 80 beta times n. My truncated functions, t beta fn, and my points x1 n. So it's this one divided by n. So divided by n. Plus another part, and another part measures how well I can approximate my regression function by the function of fn. That's 2 times the infimum over all fn, the integral of f of x minus m of x squared dx dx. And I have to tell you what I mean with t beta fn. Well, that's all truncated functions. Fn. And this truncated function is just a pointwise truncated function. Beta f of x is just beta of x for x naught. So we have a bound on the expected true error of our regression estimate for least squares estimate. The upper bound contains 2 parts. The second time measures how well you can approximate the true regression function by your function from your class. And if you forget about this factor 2, then you cannot get better than this bound. Because your estimate is in this class, so it will have an error of this form. You can't avoid this. And the second, so that's an approximation error, and that's a so-called variance theorem, which is log of a covering number divided by n, which comes from the fact that you don't observe the true function, you just observe the y-isostate. I used here that the minima exists of the empirical true risk. Of course, this does not have to exist, but it doesn't matter because you can add here some small term. Say you minimize this only of some small epsilon n, and this epsilon n then will occur in this approximation error too. And epsilon n could be of order 1 over n, and then compared with the rates you usually get, it doesn't matter. And we already made an introduction to chapter 3, and you have already seen that this error term is the right one to look at. Because the whole motivation for the regression estimation was the minimization of the L2 risk, the expectation of f of x minus y squared, and this L2 risk can be written as the L2 risk of the regression function, the expectation of f of x minus y squared, plus the L2 error, the integral of f of x minus f of x squared px dx. And this is this additional error you get. And if you are at the seminar, then you have seen this proof, this theory already more general form, but I proved this version here. Okay, questions? Okay, then let's start with the proof. Look at the L2 arrow. We have already seen in chapter 3, beginning of chapter 3, that's the L2 risk of the estimate. Minus the L2 risk of the regression function. Now I make a decomposition of this term in two terms. That's the tool. Where the second term well, that's 2 times an empirical version of this guy. And I don't have a program here, clear. It's 2 times 1 over n. So I look at 2 times the empirical risk of the regression estimate. That's why this. And T1n is just this difference of the L2 risks minus T2n. And now I bound both terms, basically the expectation of both terms, and the second one is rather easy. Well, you know that because of y is less equal, yi is less equal than beta, almost truly, the yi's are almost truly less equal than beta, and you know if you look at truncated value, how far is this truncated value of some set from y in concurrence, and how far is y? If y is bounded by beta, well, you immediately see if y is bounded by beta here, then it will be either equal to the not truncated value, then it's less than z minus y, or if this is larger than beta, then it will be closer to y than the not truncated, because the y lies in this interval between minus beta and beta. So we have this graph, which you easily see if you make this 3-case distinction, z greater beta n, z less than minus beta n, or z between minus beta and beta, or minus beta and beta. Well, if z between minus beta and beta, then it's obviously equal, but greater or less, you see it. So, but this implies that if I look at my T2n, then that's less equal if I forget about my truncation, because it's probability 1, these yi's are less than beta. So I can forget about the truncation. So I'm here. Now we have this square estimate. So that's equal to times the infimum of all Fn from applies. If you look at the expectation, then you get 2 times the whole expectation, and the expectation of the infimum is less than the infimum of the expectation. So that less than 2 times the infimum over all f in Fn. Expectation in this form. Then you see the expectation, the 1 over n, this expectation of 1 over n times something is 1 over n times the expectation. The expectation of the sum is the sum of the expectations. If you look at the expectation here, then you have the basically the L2 risk of f minus the L2 risk of m, which is L2 error. So this will be equal to 2 times the integral over f of x minus m of x squared px dx. So the expectation of T2n is this guy. So it's up this to show that's the expectation of T1n is less equal, or first term here, C1 times that is exponent 4 times 1 plus this primum m in the log L1 cover with exponent 1 divided by 8 beta n. Truncated function space points exponent n. And that we will do next week on Monday. Questions? This won't be difficult. It's basically the Wiebald-Williams theorem which we need to apply. And then you see what we need to do if we want to get some bounds on the L2 error of least squares neural network regression estimate. We have to find this or choose this function space such that both terms are small. And then you have to control simultaneously the approximation and generalization. And you will see what kind of neural network we need to get and what kind of results we get. Okay, then I'm done for today and see you on Monday.